All right, good afternoon, everybody, or good morning, or whenever you're watching this. Hello. I'm going to be walking you through the worksheet that we're going to be doing and talking about we're, why we're doing it. So what we are doing is we are going to be looking at a Bradford assay and we're going to be doing a catalytic assay again. Now, the Bradford assay, we're doing this for a couple of reasons. One, simply practice. Two, it's different. Now, if you look at the table below, I'm going to put some stars and put some markings by some of the columns that I want to draw your attention to. The columns that I first want to draw your attention to is this one right here, which is your Bradford reagent volume. That's the exact same that we previously did, 900 microliters across the board. The next column is stock volume. Now, I want you to look at, or well, before you do that, the stock volume is the stock or concentrated protein sample that we're going to use. That's the 10 milligrams per milliliter or 10 micrograms per microliter sample. And that is one that we are going to be using to prepare 4 samples. Now, the reason that we're going to be doing that is because we're not diluting that sample at all. So each one of these samples will be 10 milligrams or 10 micrograms, 10 milligrams per milliliter or 10 micrograms per microliter. Now, what this means is that if we take 100 microliters at a concentration of 10 micrograms per microliter, and we put it into a cuvette, that means we have added a grand total of 1,000 microliters to that cuvette. Okay, so if you look at your first 4 samples, we have a mixture of 900 microliters of the Bradford, a range from 25 to 100 microliters of the stock, and then we offset that total volume with DH2O, or offset that volume difference to bring us up to 1,000 microliters by adding DH2O. Okay. Now, what that will give us is that will give us amount of protein. We'll be able to use that amount of protein to generate a graph that shows absorbance at 595 nanometers on our y-axis versus protein amount or amount of protein. Protein amount. Now, that is going to be significant. Basically, these first 4 trials are very similar to trials that you did in your previous experimentation. Now, if you look at trials 5 through 7, and I'm going to erase some of the markings that I did just a moment ago, one of the things that I want you to recognize is in this stock volume concentration, well, for 5 through 7, it's 0. Then the next column is dilution number 1 volume. Okay, so where is that coming from? What is dilution number 1? Well, dilution number 1 is a dilution that you are going to make. And what I would recommend for that is to take the microcentrifuge tube that has your 10 microgram per microliter stock. And I'm going to color this red just to give the illustration. From that, make a, say, 5 microgram per microliter stock. And the way that we're going to do that is we're going to take, let's say, 150 microliters from this stock, and we're going to add it to this other microcentrifuge tube. So that's going to be the first 150 microliters. Then we're going to add an additional 150 DH2O. So it's a 1-to-1 ratio. That's making a new sample that has a concentration of 5 micrograms per microliter, half the concentration of our original sample or of our original stock. Now, one thing that I'd like to really stress here is this is in a microcentrifuge tube. This is not in the cuvette yet. We've made this dilution so that we can make samples 5 through 7. So from this, and I'm going to erase my stock and any information related to my stock. So I have this new dilution number 1. And with that dilution number 1, I'm going to get my cuvette. I'm going to add 900 microliters of DH2O. or I'm sorry, 900 microliters of my Bradford reagent. Then I'm going to add 50 microliters of dilution number one. And to that mixture, I'm then going to add 50 microliters of DH2O. Okay. So what that will allow me to do is then fill in this blank over here. So 50 microliters at 5 micrograms per microliter is going to give me 250 micrograms of total protein. Now, you might be looking at this and thinking to yourself, well, why? Well, one reason is we are developing a graph that shows amount of protein versus absorbance. So what that will allow us to do is kind of backtrack and calculate the concentration of an unknown sample. So what this will also do, this will provide us with some more data points that we can use to get a line that maybe captures a wider range of amounts of protein. So in addition to that, samples number 4 and 5, they should be very similar to one another. They have the same amount of protein, and so their absorbance should be very similar to one another. So this is kind of an internal check. So for samples 5 through 7, what we're going to be doing is making a 5 microgram per microliter stock, or sorry, dilution. That's dilution number 1. Now, dilution number 2, I would recommend taking 150 microliters from that to make dilution number 2. And these are rough numbers. And whenever I say rough numbers, it might be easier for you to do 200 microliters of the stock plus 200 microliters of water and so on. But this is just an illustration. So for dilution 2, it's 150 microliters from the stock, from dilution number 1 plus 150 DH2O. Okay, so this dilution number 2, the way that I've described it and designed it here, would have a concentration of 2.5 micrograms per microliter. And then what we can do is fill out, okay, well, if we have 50 microliters of dilution number 2, 50, I'm going to go over to the right-hand side of the screen, 50 times 2.5 gives us 125 micrograms of protein. So this is a table that you have a little bit of freedom and latitude to use. Your dilutions do not have to be one-to-one dilutions. They can be whatever you want them to be. The important thing is that you know what they are so that you can calculate your amounts of protein for samples 5 through 10. Now, the angle of this curve should look very similar to the curve that you've previously produced as a Bradford assay. Now, what makes this a little bit different, and the benefit of this is, let's say hypothetically that you get a protein sample that, somebody brings you a river water. And you take that river water and you take 100 microliters of that. And you add it to the 900 microliters of Bradford. You can solve for protein amount. And let's say that it's 2.6 micrograms. Now that amount of protein is going to be very, very low. The concentration of that sample is going to be very, very low. But the benefit of this is that you can very easily figure out the concentration of that sample by saying, well, I know it was 2.6 micrograms of protein. And what was my volume that I used? It was 100 microliters, because I took 100 microliters from my river water and added it to my Bradford reagent. And there we go, 2.6 divided by 100 microliters. Okay, this is also helpful because there's a time that you might deal with a sample that gives you an absorbance that is outside your linear range. And then you'd have to make a dilution. Say if you get 100, let's go ahead and go to a slightly different scenario. Let's say that you get 100 microliters of DH2O from the river, and you, or not DH2O, 100 microliters of river water, you add it to 900 microliters of the Bradford reagent, and you get an absorbance of 4.00 or 4.000. That's going to be far outside the linear range. I feel comfortable saying that. Like that's too high of a number to actually get any information from. So with that sample, you're going to say, well, this protein sample is far too concentrated to work with. So then maybe what you'll do is you'll say, all right, well, let's go ahead and say 10 microliters of this. I'll take 10 microliters, I'll add it to 90 microliters of DH2O, and that combination I will add to 900 microliters of Bradford reagent. Now, whenever I have that combination there, let's say that my absorbance ends up, or let's say that my amount of protein ends up being, let's say 275 micrograms. It's 275 micrograms. Your absorbance would end up somewhere here between these two samples. And then you'd be able to say, well, I know the concentration of this because I know that all of my protein was from this 10 microliters. So I'm going to say 275 divided by 10 microliters. And that's where you end up with your amount or your concentration of that protein sample. All right, so that's the first part of our experiment. The next part of our experiment is going to be doing catalytic assays. And so for our catalytic assay, we have a total of 4 samples that we're going to be evaluating. We have our whole cell extract. We have our 15,000 RPM sample. We have our 40% cut. And then we have our 65% cut. And so, that actually, sorry, that's our pellet, our last one. So what we are going to be doing here with each one of these samples is testing for whether or not they have any enzyme activity. Because we want to know, well, where is our enzyme? Like we're trying to purify lactate dehydrogenase. Which sample do we need to look at? Do we need to start with our whole cell extract and move forward with that? Or do we need to just abandon that and say, oh, well, as it turns out, we have a high concentration of our enzyme in the 15,000 RPM, or the highest concentration is in that sample. So this mixture, what we're going to be doing is we're going to be measuring absorbance at 340 nanometers. We're going to be using absorbance at 340 nanometers because of the fact that at A340, just a second, at A340, we have, absorbance at 340 nanometers. What we see is the absorbance of the molecule NADH. So our enzyme, lactate dehydrogenase, takes NAD plus and lactate and makes NADH and pyruvate. Now, NADH will absorb light at 340 nanometers. Pyruvate will not. NAD plus will not. Lactate will not. So effectively, as long as we're seeing the concentration of NADH, the absorbance at 340 nanometers increase, that's an indication that we have LDH activity. That means that we have lactate dehydrogenase in that particular fraction. Now, in order to evaluate this, I'm going to use this first one as an example. We're going to be looking at our whole cell extract, we're going to do two different trials of it. We're going to be looking at 50 microliters of the enzyme versus 25 microliters of the enzyme. Now, what we will need to add to all of this is the enzyme buffer or CAPS buffer. That buffer has a pH of 10 and is approximately 150 millimolar. So that CAPS buffer, what we're going to be doing is we're going to be adding to a UV cuvette. Look at that. That's an awesome rectangular prism. We're going to be adding NAD plus, lactate, and CAPS. Now we want that volume to be 950 microliters for the first three trials. Because the last thing that we're going to add is 50 microliters from that whole cell extract. So we saved 1 milliliter of our whole cell extract, and here we're going to be doing 1, 2, and 3 trials with that whole cell extract. You will do this. So what that means is since we have 4 samples, you're going to do 2 volumes for each of those 4 samples. So that means 8. And for those total 8, you're going to be doing 3 different trials. So that means you're going to be doing enzyme assays approximately or roughly 24 times. What you're going to be monitoring for is you're going to be monitoring as that absorbance at 340 nanometers changes over the course of 60 seconds. So you will put the enzyme fraction into the cuvette, press read sample at 0 seconds, then with a watch or a timer of some sort, count to 15 seconds, press read the sample, 15 seconds, press read the sample, 15 seconds, read the sample, 15 seconds, press read the sample. I want your timing to be based on when you get a result from reading that sample, because if you base it on, well, I'm going to press read sample, what you're going to hear is the spectrophotometer making some noise. And it's actually beginning to read. You'll press read sample. 15 seconds later, or sorry, several seconds later, you will get a display with the absorbance at 340 nanometers. As soon as you see that display, record it and simultaneously press read sample. In the event that you press read sample and wait 15 seconds, it's possible that you will need to, or you will be pressing it almost immediately after. At any rate, this is what you're going to be doing for those samples. That's approximately 24 samples. You may want to do one over again. But what you're going to monitor is the change in A340, the change in absorbance in 1 minute. So you'll basically take the 60-second time point and subtract it from the 0-second time point and divide it by 1. All right, everybody. I hope that was helpful, and I hope you all have a wonderful afternoon, and I will see you later.